The diagram shows a sketch of part of the curve C with the parametric equations x equals t squared plus 1 and y equals 3 times 1 plus t. The normal to the curve at the point P, 5, 9, cuts the x-axis at point Q. Find the x-coordinate of Q. Right, so the normal cutting the x-axis. So if I work out the equation of the normal, I can find where that cuts the x-axis because y will be equal to 0. For the equation of the normal, I want to differentiate to get the gradient of the curve at point P. And then I can do the negative reciprocal to get the gradient of the normal, and then do y equals mx plus c. So let's get our gradient function. So we can see here, because we've got parametric equations, I'm first going to differentiate to get dx by dt. So differentiating t squared plus 1 will give me 2t. Now to differentiate the y function, so dy by dt. So just to help me, I'm going to expand this bracket. Differentiating 3 plus 3t, I'll get 3. So therefore, my gradient function is the dy by dt. I know dy by dx is equal to dy by dt divided by dx by dt. So it's 3 divided by 2t. So that's the gradient function in terms of t. Now to actually work out what the gradient is at point P, I'd like to know what t is at point P. Now I don't know what that is just yet. I know the x-coordinate is 5 and I know the y-coordinate is 9. So if I use that's coordinate, so I could say that 5 equals t squared plus 1, so making my x-coordinate equal to t squared plus 1. And also my 3 plus 3t is going to equal 9. I'm going to continue with the y function here because that's linear. It's only going to give me one answer, whereas the quadratic one there will give me 2 different values for t, so I wouldn't know which one to pick. So just continuing with the linear equation, take the 3 away from both sides, so I find that 3t is 6. So therefore t is 2 at point P, which means the gradient is 3 over 2 times 2, or 3/4. So that's the gradient of the curve at point P. I want the gradient of the normal now. So the normal is going to have a negative reciprocal gradient, so minus 4 over 3. I can now do y equals mx plus c. Substituting in the coordinate that the normal goes through, which is 5, 9. And working out what the y-intercept is going to be. So 9 plus 20 over 3 is going to be 47 over 3. So the equation of my normal then is y equals minus 4 over 3x plus 47 over 3. That's the equation of my normal. Remember, I'm trying to work out the x-coordinate of Q, which is where y equals 0. So let's make y equal to 0 here. Times through by 3 to get rid of these awkward fractions. Move the x to the left-hand side. And I find that the x-coordinate is 47 over 4. So that's my answer to part A of this question. Let's move to part B. So we just found out that point Q here, the x-coordinate was 47 over 4. Right, part B. Finds the area of the finite region of R bounded by the curve C, the line PQ, and the x-axis. So basically this shaded area. I need to draw a vertical line at point P because I can find all of this shaded area here by integrating the curve. This region is bounded by the curve, the x-axis. So I can do this by integrating. Then I have a triangle that I can work out. And then I can add my two answers together. So this is my method. To help me out with this, let me mark on some of the other information I already know. I know point P is the coordinate 5, 9. So for this triangle, let's do this triangle first actually, because that's going to be nice and easy here. So the x-coordinate here is 5. So therefore I can do the base of the triangle will be 47 over 4. That's the same thing as 11 3/4. Take away 5. So the base of this triangle is 6 3/4. The height of the triangle is 9. So we can do half base. So 6 3/4 times height. And we can then work that out. So just getting a calculator. So 6 3/4 times 9. Divide by 2. So the area of that triangle is 243 over 8. Let's now move to the yellow shaded area here that we're going to find by integrating. So, because we're integrating parametrically, we need to do the integration of y times dx by dt. Now our limits, we need to figure out what the t limit is here. And we already know the t limit at point P was 2. So we know that our upper limit of t is 2. At this point here, at the lower limit, we know that's where y equals 0. So if we look at our y function here, we can see that's going to equal 0 when t equals -1. So that's our lower limit for t. Oops. Right, so let's substitute in. The y we know is 3 plus 3t. The dx by dt, we've already worked that out previously. We've already differentiated this once and got 2t. Let's expand that bracket. So we'll get 6t plus 6t squared. Which when integrated will get 3t squared plus 2t cubed. Substitute the 2 in first, so 3 times 2 squared plus 2 times 2 cubed. Take away 3 times -1 squared plus 2 times -1 cubed. And we will work this out. So that's going to be 12 plus 16 minus 3 minus 2. So 28 minus 1 is 27. So that is the area there. So the total will be 27 plus the 243 over 8, which gives 459 over 8. And that is my answer.